Hi, my name is Shelley Bruce, and I'm going to be speaking on chemistry today. I know I have it all up in my face, and I'm sorry, but the last time we spoke, my microphone was not picking up well, so I'm doing it this way, hoping that the volume is picking up. I am going to talk about specific heat, and this time what I did was just make the handout, so I'm going to show it to you as though it's on PowerPoint or Google document. I would use obviously some form of technology for this and provide the handouts to them and work through it with them through Canvas or whatever tools you want us to use. I I want to be able to just work through it. So I'm a little hung up on this time thing because I'm going to do my best. Okay? 5 to 10 minutes, I can do it and follow along. Here's the thing with them. This would come at the time of the year that I want to already have covered gas laws, heat, entropy, thermodynamics. I would have already talked about Q equals MC delta T. And I have all these equations out for you. So I'm going to show it to you kind of the old school way. I have made myself little flashcards, index cards, and I would have it available through Google Docs, as I already said, PowerPoint, some form. And I would have my handouts. I would type it up, have it for them, see if I can show it to you on here. But I would talk about specific heat of water, which gives us the calorie. The calorie, by definition, is the amount of heat it takes to change 1 gram of water, liquid water, to increase its temperature by 1 degree Celsius. That is the calorie. Now, that's not the food calorie. The food calorie we understand is like a kilocalorie. It's the amount of heat needed to raise the temperature of 1,000 grams of liquid water by 1 degree Celsius. But the calorie we're going to use in the chemistry labs, by definition, that is definition is the specific heat of water, is the amount of heat it takes to move 1 gram of water 1 degree Celsius. Now, when we talk about heat energy, we generally do things in joules, not in grams. So for today, we're going to use the joule numbers, and I have that for you, what I'm going to show you on here. There you go. The C, the students would have already covered this. So the C is a specific heat of steam, would be 2010 joules, the amount of heat it takes for 1 kilogram of steam to go up 1 degree Celsius. Specific heat for liquid water is the 4,186. It takes that number of joules to go up 1 degree Celsius for 1 kilogram of liquid water. And the number is 2,090 for ice. Now, the way this works with the problems when you get into the chemistry book, the lab, and they're like, whoa, you see these math questions, and the students, they're immediately overwhelmed. They don't know what to do with it. And I feel like my job as the instructor or the facilitator is to help them just break it down and make it so doable. So here's my question. I wrote it out for you, kind of old school way, flashcards. And again, just pretend this is my PowerPoint or screen through, okay? How much heat, energy, would I need to change 2 kilograms of ice at a negative 10 degrees Celsius into steam at 120 degrees Celsius? Now, this is understanding that this is going to be in a closed system. So I'm going to drop my ice into some water, and I'm going to heat it up. And I'm going to catch my steam. This is my steam collector, and my steam is not going to lose heat into the air. It's going to be collected, and I'm going to raise the temperature of that steam, all 2 kilograms, up to 120 degrees Celsius. Now, this takes 5 steps. Okay, 5 steps. We're going to go from a phase chart, which you've already seen this. So this is not, getting into your 5-minute little lesson, because you had this yesterday, day before, last week. You've already seen this phase change diagram. You've already talked about how to heat things up, you're going to go from solid to liquid to gas. Now, to cross from a solid into a liquid, you cross what they call the heat of fusion. I've got right there, heat of fusion. And the heat of vaporization, to vaporize, goes from my liquid water up to my steam. Now, how do I find these? I wrote it out on here. I put it on a different card. It's a little bit easier to follow as you go straight across instead of up the slope there. So here's the card. If I'm going to have a change in temperature, this is my Q1, Q3, and Q5. This is from my my -10 to 0. I'll do a change in temperature with the specific heat of ice, mass of 2 kilograms. My liquid water, change in temperature, 0 to 100, specific heat of liquid water, mass of 2 kilograms. My Q5 will be a change in temperature from, this is my steam, from 100 degrees up to 120 degrees. So a 20-degree change, specific heat of steam by 2 kilograms. And I'm going to have 2 phase changes in this problem. I'm going to change phase from my solid ice, stays the same temperature, changes into liquid water. My liquid water gets hot, MC delta T, I'm going to change my temperature to 100 degrees. Hit 100 degrees, I need to vaporize. I'm going to do heat of vaporization is Q equals mL. Which I have on this paper. L is my latent heat. We've already done this part. This was yesterday also. So I'm kind of throwing you in the middle of a problem that I just enjoyed doing these problems, so I wanted to kind of show you some of it. This is my latent heat. And this is the hidden heat. Latent heat is hidden heat, and it's just a change of phase. It's something you don't see. It's hidden heat. You have to add heat to change your solid ice, to break the molecule, and to break to expand the bonds, the hydrogen bonds, from the solid to the liquid. And you do it again from the liquid into the gas. So this is just a change of phase kind of equation. That's why you only have it here at the ice to liquid, and here again from liquid to steam. Okay, so to begin this problem, I'm going to show you all the numbers that you need first. Alright, here are my numbers. Here's my vapor, 2,260,000 joules per kilogram, and fusion, 333,000 joules per kilogram. I'm going to need my specific heat of water numbers, my specific heat of steam, again 2010, liquid 4,186, ice 2,090. I'll break this into 5 parts. I go and over the fact that the students should write down all 5. And when you do it, when you get to the end, you still write all 5, because the one that falls in the crack is what makes you miss the problem. And this is so easy if you'll just follow the steps. So you have Q1. This is a little difficult working with this camera, so please, again, pretend I'm on VoiceOver, PowerPoint, something like that. All right, so here's my ice. Q is MC delta T. M, the C of the specific heat of ice. Change in temperature is 10 degrees. Gives me 41,800 joules. From ice to 0 degrees Celsius. Now I'm going to have to do a phase change. I'll put that on the next page. I'm a liquid water of 0. I'm going to move it up to 100 degrees. So my MC delta T this time is 100 degrees. I cross out my units. I have time to go over that with the students in class too. Cross out my units. I'm going to end up with heat in joules. Q3 is 837,200 joules. Q5, steam, MC delta T, change in temperature from 100 degrees to 120 degrees is a temperature of 20. I do my MC delta T, end up with 80,400 joules. Okay, so I'm going to do Q2 and Q4. My Q2 is mass times the latent heat of fusion. Is that number I just showed you? And this is something the students would have already be familiar with. I'm just helping them put together this phase change diagram for the water type problems. And then we've already heated the Q3, got it up to 100 degrees, and now I need to change it into steam. That's called heat of vaporization, Q4. The heat of, this is step 4, the heat of vaporization. I'm changing from liquid into steam. That's mass times latent heat of vaporization. There's the number off the page, and I'm off your screen. There you are. Multiply 4,520,000 joules. Now I'm going to put it all together. My question again, what is the heat needed to change 2 kilograms of ice at -10 degrees into steam at 120? How much heat would that take? I would do a phase change diagram. I would explain to you that first you're going to start with your ice and you're going to get a little bit warmer. You're going to go up to 0 degrees. You've got to change your ice into liquid. That is a hidden heat. It doesn't change your temperature, it just changes your phase. That's Q2. Q3, I'm going to take my 0 degrees and go up to 100 degrees. That's my liquid water. Q4, my liquid water changes into steam. That is the latent heat of vaporization. Q equals mLV. And now that it is steam, I'm going to heat it up to 120 degrees. Q is MC delta T. So I have 5 heat changes. This is a fun trick with my pencil. Here are my 5 steps of the joules. I'm going to add it up. I get a total heat needed for the 2 kilograms to go from -10 all the way to 120 degrees Celsius, 6,145,400 joules, and change it into kilojoules by dividing by 1,000. You have your answer. I went over this so many times in trying to think of, the way to work you through it in 5 to 10 minutes. There's a lot of assumptions that we've already covered a lot of this during class time, that I won't cover that. Again, I don't want to duplicate myself too much during this short video, but I would conclude with just going over the equations again. I would conclude by explaining the 5 steps. How do I know my 5 steps? What do I do when I see the next problem? How do I get there? How does this apply to real life? How does this apply to the laboratory? Walking out on the beach, the sand, it gets hot, but it doesn't absorb it. My feet get hot, it reflects it. But the water, the neat thing about water, God did an amazing thing when He made this earth and put so much water on it. He used the water to help regulate the temperature. Water has higher specific heat than any other common substance, and that's just something amazing about it, and it kind of makes it a lot of fun to do this type of problem. I hope you've either learned something or maybe it was a review for you, but I hope you enjoyed the video. Have a good day.